So Stephane graduated from the École nationale supérieure de chimie de Paris in 1998, and he obtained his PhD in 2002 from the University of Angers under the supervision of Patrick Bataille. He was awarded a Lavoisier Fellowship for a postdoctoral stay in the group of Professor Long at UC Berkeley. And then in 2004, he took a CNRS researcher position in Strasbourg. And in 2009, he was habilitated and promoted director of research in 2019. In 2011, he went to GSPS fellowship in the group of Professor Kitagawa in Kyoto. And in 2019, he had an USIAS fellowship. And to sum up, his scientific interests are coordination and supramolecular chemistry and deep eutectic solvents. And today, we will talk about non-covalent interactions, so silver P interactions in dipyrrin-based assemblies. So please, Stephane.
Thank you very much, Sylvie, for the kind introduction. And of course, I'd like to thank Jean-Pierre and the organizer for giving me the opportunity today to present some of our research. So our research is dividing in three main axes. The first one focuses on metal organic frameworks, and in particular, the development of conducting materials, trying to combine porosity with the electronic transport. To that aim, we are developing tetrachiafluvaline and forming coordination polymer and strategies towards controlling their assembly in the crystalline state. Another research axis we are developing is focusing on deep eutectic solvents, which are sort of cousins of ionic liquids towards the formation of metal organic framework in this new greener medium. But the main axis I would talk about today is focusing on dipyrins and their use for the construction of coordination polymers. So what are dipyrins? Dipyrins are a conjugated bispyridic backbone shown here. They're actually an oxidized form of dipyromethane, which is a very common intermediate in porphyrin chemistry. The particularity of its derivatives is that they can be functionalized either at the periodic positions, 1, 9, which correspond to alpha position, 2, 3, 7, and 8, which are equivalent to beta position of a porphyrin, and as well as the so-called position 5, which corresponds to the meso position of a porphyrin. Another feature is that under a mild basic condition, they form a monoanionic chelate, and this monoanionic chelate can be used for the complexation of a whole variety of transition metals and metalloids. And in particular, you may have encountered body P derivatives, which are very heavily studied in literature for their photophysical properties and rather high emission. When it comes to transition metal complexes, we can find two main applications. The first one is, as for the body P, the investigation of the photophysical properties. So we can show here this homoleptic zinc complex, which has been reported to be luminescent by the group of Jonathan Lindsay, and also playing with a dipyrin backbone and appending two phenol rings. Here can be prepared sort of a silane type dipyrin-like ligand, and the group of Nabeshima has showed that these aluminum complexes can be also highly emissive. Another application of those derivatives is their use for catalytic application or for their catalytic activity, and you recognize here the same backbone, but in this case, this is a manganese-free complex that has been studied by the group of Oculo and Andrioletti for epoxidation. Another key player in this field is the group of Bentley, who have elegantly developed iron 2 and all sorts of other metal complexes for CH elimination or CH activation reactions. Our interest in those types of ligands actually comes from the independent report by Lindsay and Dolphin at the end of the 90s that they showed it was a way to readily synthesize dipyrin ligands, where the alpha and beta position here are non-functionalized, so they have hydrogen atoms in those positions, and they bear in the so-called position 5 an aromatic ring. And you can see here the schematic representation of a cobalt-free complex and the crystal structure of this compound. So the particularity of those compounds is that they are rather stable. They can be purified by column chromatography and be readily isolated in good yields. And we saw here the aromatic ring as a way to, as a platform to introduce a secondary coordination site to develop differentiated ligands. So you can see here examples of such ligands, dipyrinato ligands bearing a benzoic acid group, a benzonitrile, a pyridine, or a phenylimidazole. And playing with those ligands, one can envision to construct coordination polymers. For example, if one considers the dipyrine bearing a pyridyl group in the position 5, assembly with copper acetylacetonate leads to the formation of this type of heteroleptic compounds with, on one end, an acetylacetonate, a dipyrinato on the other end, and pendant pyridyl group. Upon self-assembly, this type of compounds does form a one-dimensional coordination polymer by coordination of a pyridyl group to a neighboring copper cation. Also, the formation of homoleptic complexes can be considered in this case, such as the analog of a cobalt complexes I just presented in the previous slide. You have a complex bearing at the periphery 3 different coordinating units, which can be used for the coordination of a secondary metal center. Here, one can envision the formation of honeycomb-like architectures. And so those are based on examples reported by the group of Seth Cohen, where they have described this type of one-dimensional coordination polymer in case of a copper, and assembly of a cobalt complex with a silver 1 cation leads to the formation of this honeycomb-like network. And it's worth emphasizing here that the coordination around the silver cation involves here only the peripheral pyridyl groups. In our case, we have also investigated this type of construction of coordination polymers with a whole variety of ligands, and I'll come back to that later. But again, we can take as an example the dipyrine-pyridine derivative. We have shown that upon reaction with copper-2, palladium-2, or zinc-2, we can form sort of a metal complex that is an analog of 4,4' bipyridine, with 2 pyridines here at the periphery that can be assembled with iron-2 or cadmium-2 units to form this type of heterometallic 2-dimensional coordination polymers. Interestingly, the formation of such networks can also be done not only in a stepwise fashion, but also in a one-part mode by mixing the ligand with a combination of those 2 metal salts. You have a selection of a copper, palladium, or zinc for the dipyrinato fragment, while the pyridine does coordinate either iron-2 or cadmium-2. When the first step is done with cadmium-2 or nickel-2, we have a formation of complexes that tend to actually increase their coordination number, going from 4 to 6, leading to self-assembly and the formation of homometallic coordination polymers. Interestingly, those coordination polymers can be disassembled and reassembled into another architecture by playing with a chelate effect. Reaction of this type of network in suspension with a chelate leads to the formation of a heteroleptic complex that can then be subsequently self-assembled or assembled with another metal complexes, such as cadmium-2, leading to heterometallic architectures. So you can see here, this strategy works quite well. And this is almost, if you've done synthesis, you know that sometimes some reactions don't work as planned. And this is actually exactly what I would like to entertain you with today, is when this strategy doesn't work as well as is shown here. And it leads to surprising results, at least for us at the beginning. And now we build from this. And this is where silver pi interaction comes into play. Because one of the first results we obtained was to use the zinc complex bearing nitrile groups at the periphery, and we assembled it with a whole variety of silver salts. We obtained crystalline material, and this is the crystal structure of such a heterometallic system, where you have here in orange the silver cation that is coordinated to the peripheral nitrile group of a dipyrine ligand, triflate anion, but the silver cation also tends to sit on top of a carbon-carbon double bond of a pure Lake system with a distance of 2.4 to 2.6 angstroms. And this type of organization is actually suggestive of silver-pi interaction. So this was actually unexpected for us, although silver-pi interaction per se are not a novel interaction. Actually, they've been suggested about 100 years ago by Hill when he was trying to determine the molecular weight of silver perchlorate in benzene. What he showed, what he obtained were actually surprising results, and he suggested back then that there was a specific interaction between the benzene ring and the silver cation in this case. This was later confirmed by Smith and Rundle in 1958 when they actually determined the crystal structure of this material, indeed highlighting that the silver sits on top of a carbon-carbon double bond with a distance of 2.5 to 2.6 angstroms once again. This was later heavily investigated in literature with a whole variety of aromatic systems and polyaromatic systems. We can here show the assembly of an anthracene with silver perchlorate once again, where you see a rather complex network of silver-pi interaction and coordination of a perchlorate anion. So the group of Cauchy went into trying to determine the coordination, the geometrical parameters of this interaction by studying a series of cyl-stilbenoate derivatives and their assembly with silver cation. What they've shown with those systems is that the silver cation is complex or is interacting with a carbon-carbon bond, either in an eta-1 or a dissymmetrical eta-2 complexation, with a distance to the average plane of about 2.4 angstroms. And so if you would consider a classical model, you would expect actually the silver to sit on top of a carbon-carbon double bond in an eta-2 mode. And as you can see here, this is not experimentally what is observed. This has been recently rationalized by the group of Liu and Rogachev in this paper, where they showed that there were different contributions, indeed, as expected for this interaction. The main one is the ligand to the metal contribution, as shown here. But this secondary contribution that determines sort of the way this silver cation sits on top of a carbon-carbon double bond depends on the nature of a carbon atom or the coordination site that is involved. When we have a dxy orbital that is more involved, you have a tendency to eta2 complexation. While this is a dz2, you have more of an eta1, and this is usually what determines whether you have one or the other. But the examples I'm showing here are mostly polyaromatic systems. And what about pyrrolic derivatives? As a matter of fact, these pyrrolic derivatives have been mostly studied in solution. So we can cite here the very elegant work by the group of Dolphin, where they studied these dipyrrin ligands. So you can recognize here the dipyrrin fragment that I mentioned earlier. Two of those are bridged by an ethylene group. A methylene group, and upon complexation of zinc cation, they form helicates. You have here a schematic representation of this helicate, and in this case, a crystal structure of this compound, with one strand in black and one strand in gray. And so they were trying to investigate whether in these complexes you can form more of a P or the M helix, whether you can have an enantiomeric enrichment of those helices. And to do that, they studied by NMR the assembly of those complexes with silver salt and the presence of a chiral lanthanide salt. And they showed in their NMR investigation that indeed there was an interaction of a silver cation to the carbon-carbon double bond in this system. Another example of a solution study that is worth highlighting is the elegant result by the group of Seiji Shinkai, where they investigated the assembly of this double-decker serum porphyrin system, where you have two porphyrins sandwiching the serum-4 cation, and they investigated the assembly with silver 1 salts. What they observed by NMR, Raman, and UV visible spectroscopies is that indeed there was an interaction of a silver cation to the beta-pyrrolic carbon-carbon bond in this system. So while there were those solution studies, in terms of observation in a crystallite state, this was way more limited at the time we studied this work. As a matter of fact, to the best of our knowledge, there was only one example that has been reported by the group of Ma, where they investigated this type of ligand and its assembly with silver nitrate. They obtained a crystal structure of a resulting network, and they showed that in this case, the silver sits not on top of a carbon-carbon double bond, but on top of a carbon-nitrogen bond with a distance of about 2.6 to 2.7 angstroms. And this is worth remembering because I will come back to that. So it seemed to us that while this had been heavily investigated with aromatic system and polyaromatic systems, actually there were way less results or reports with pyrrolic systems. So we went on to study all our complexes and investigate their assembly with silver 1 cation. And Domingo Salazar, who was a PhD student at the time, obtained results here with heteroleptic copper complexes or homoleptic copper complex. And in both cases, he obtained a rather complex set of coordination polymers, where once again, the silver is coordinated to the peripheral nitrile, as we had anticipated, but also interacts with a carbon-carbon system, carbon system of a periodic skeleton of a dipyrine. So either in a combination of eta 2, eta 1, or with two eta 2 systems. As you can see, this is rather versatile depending on the type of organizations. So it seems that this can be observed indeed with the zinc tetrahedral complex, but also with copper square planar or pseudo tetrahedral complexes too. So we went on to see whether this could be observed also with octahedral species. And this is indeed the case for those heteroleptic complexes. You can see here this complex with a cobalt hexafluoroacetylacetonate with two dipyrines, or this cobalt silane with one dipyrine. In both cases, assembly with silver salts showed the presence of silver pi interaction, in this case in an eta 2 fashion for this coordination polymer, while with a cobalt silane compound, what we observed was a metallamacrocycle, where we have two cobalt complexes interacting with two silver 1 cation via silver pi interaction, with a distance once again of 2.4 to 2.6, 2.65 angstroms. So this is interesting to note that in this case, we do have this interaction, even though this is with an octahedral cobalt complex, because as I mentioned before, the group of Cohen has elegantly studied the assembly of homoleptic cobalt complexes with silver 1 cation, as shown here with the same ligand as the one we've just described. And in this case, they have no silver pi interaction in their crystal structures. So this was rather surprising to us. Maybe it's because of the geometrical organization of a periodic system around the metal. You see here a rather regular coordination sphere, while in the case of our heteroleptic system, this is much more open. You have here sort of a distortion around although the coordination geometry is really octahedral around the cobalt system, around the cobalt cation. You do see a flattening of the organization around the nitrogen-nitrogen axis. So after observing this interaction with zinc, copper, and cobalt cations with a whole variety of coordination environment of a metalloligand, we went on to ask ourselves a rather genuine question: what does the ligand alone do with silver 1 cations? And it turns out that in this case, we did observe the formation of 2+2 metallamacrocycle upon complexation of a peripheral nitrile to the silver, but involvement of a pyrolytic system here with a puro-nitrogen interaction. In this case, we don't have a presence of silver pi interaction, and we have prepared a whole series of those metallamacrocycles with a diverse set of ligands bearing instead of a benzonitrile, a pyridine or a phenylpyridine or phenylimidazolide. And recurrently, we do observe this type of interaction, this type of organization, and no silver pi interaction. So as you've seen here, we have observed this interaction mostly with nitrile groups, dipyrine-bearing nitrile groups at the periphery, and then we went on to investigate a diverse set of ligands. And Dmitry Pogozev, who was a PhD student at the time, prepared a whole bunch of those ligands, either bearing pyridyl groups, pyrimidine, phenylpyridine, phenylimidazolide, or phenylpyrazolide. He prepared metal complexes of those ligands and also studied their assembly with silver salt, obtained heterometallic architectures. But surprisingly to us, in this case, we had what we had anticipated at the onset of our study, only the coordination of a peripheral group to the silver 1 cation and no silver pi interaction. So we went on with 4 years without observing this interaction with this set of ligands. And we wonder at the time whether it was not because those ligands were more strongly coordinating than the nitrile, and the silver had a complete coordination sphere in this case. It turns out that actually we were probably wrong, because one day, while we were studying this heteroleptic copper complex bearing here an acetylacetonato ligand with 2 pyridyl unit and a dipyrine with a pyridyl unit at the periphery, the ligand that you've seen before, Antoine Béziot observed this two-dimensional coordination polymer where the silver is coordinated to the 3 peripheral pyridyl groups, forming two-dimensional sheets. But those sheets do stack in the crystalline state by a silver pi interaction, with a distance here between 2.6 and 2.8 angstroms. So even though we were in the coordination involves pyridyl groups, in this case, we do still observe a silver pi interaction, although with longer silver to carbon distance. So even with those type of ligands, we can observe this mode of assembly. And this seems that there is a fine balance between the presence of the absence of this interaction, because indeed, when we are using this heteroleptic cobalt complex and we assemble it with silver cations, we observe polymorphism or pseudopolymorphism in this case, where we have different types of crystals within the same batch. In some crystals, we do not observe silver pi interaction, only coordination of the acetonitrile molecule with the free pyridyl units. And in other cases, eta 1 mode of assembly of a silver to the carbon-carbon double bond. So we went on to see whether we could generalize that to other type of system, and not only metal complexes, but also body P derivatives, and also see whether the functionalization at the periodic system could have an influence. So Fan Zhang prepared this body P derivative, bearing here a methyl group, sorry, and assembled it with silver 1 cation. We obtained 2 + 2 metallamicrocycles, and those metallamicrocycles stack in the solid state by a silver pi interaction, or at least let's say that there is a silver carbon distance that suggests this interaction with a distance of 2.8 to 2.9 angstroms. So this is interesting to see that even in this case where we have a methyl group, the interactions that we observe, or the mode of assembly, always involves the carbon-carbon bond, what would be equivalent of a beta-pyrulic carbons for a porphyrin. And this struck us because if we come back to this original result that I showed you from the group of Ma, where they reported that the silver sits on top of a carbon-nitrogen bond, our results were at variance with this observation. So we started looking a bit closer at this crystal structure. And if we look at the ellipsoid of this structure, we do see that actually there is an odd organization of the nitrogen and the carbon in this case. And maybe this suggests that there's been a wrong assignment of a carbon to the nitrogen, and this would be indeed the carbon, and this atom would be the nitrogen, making it a carbon-carbon double bond interacting with a silver cation, which would be consistent with the result we have observed in our study. So we went on to remake this ligand and study its assembly with silver 1 cation, redetermine the crystal structure, and indeed, what we observed was a carbon-carbon bond interaction with the silver 1 cation. We also studied it with a whole variety of silver salts, and in all instances, this was the same mode of assembly, which is consistent with the results we have observed with our dipyrrin ligands. So as you can see, we do observe this interaction, but we don't really have we are sort of dependent on whether it's present or absent. And all we can do is put the ingredients in our metal complexes to hope that this will be present. But this is a bit complicated in terms of trying to design types of coordination polymers. So we went on to try to see whether we could address the silver pi interaction, and if we would be able to do so, whether we could promote or control it. In that case, one could hope to form heterometallic coordination polymers using solely this interaction, in analogy with what had been reported in the 90s by the group of Munakata, where they investigated polyaromatic systems and their assembly with silver 1 cations, such as the silver triflate salt, which forms a binuclear unit that is bridged by this hexaphenyl benzene. So to do that, we went back to the original solution studies that I mentioned earlier. In the solution studies by the group of Seiji Shinkai, they had studied this double-decker serum porphyrin system and its assembly with silver 1 cation. And they had this one representation of this compound, and they showed what they called the B pocket, which corresponds to two periodic systems that are facing each other and would favor the silver pi interaction. And we thought, maybe naively, that indeed having two periodic rings arranged in such a fashion, maybe we could favor the silver pi interaction in this case. So we wanted to redesign our ligands, and to do that, we thought of going from dipyrrin to 2' bis dipyrrin ligands. This type of derivatives has been studied by the groups of Dolphin, Maeda, and Breuring, and they consist of two dipyrrin fragments that are directly coordinated in the position 2 and 2' by a carbon-carbon bond. Upon complexation of zinc 2 cations, they tend to form binuclear helicates. So you have one strand here in the front and one strand in the back. And what was of interest to us is that if you look at this type of helicates, they actually have 4 pairs of periodic systems that are facing each other, but are arranged in an analogous fashion to what is observed in the double-decker serum porphyrin system. Also, this type of compounds had not been studied in literature for the assembly with silver 1 cation, so we thought that maybe there was an opportunity to do so and to complement our study. Another interest in those ligands is actually their synthesis starts from the monodipyrrin ligands. So in a multi-step way, we went from our original ligands and we prepared this binuclear zinc helicate and characterize it and also crystallize it. And you see here the organization of the 2 strands around the 2 zinc cations. We then studied its assembly with silver 1 cation, and what we observed that indeed the silver 1 cation is being complexed by the helicate with a silver 1 sitting between 2 periodic systems as we had hoped and anticipated. Interestingly here, the peripheral nitrides are not completely in the coordination sphere of a silver 1 cation. This is the triflate anion and the THF solvent molecules from the crystallization system that complete the coordination sphere. So playing with those two, the anion and the solvent, we were able to go from the discrete tetranuclear system to coordination polymers. Indeed, replacing THF by acetyl ethyl acetate, we obtain one-dimensional coordination polymer, still with this recurrent tetranuclear motif with 1 helicate and 2 silver 1 cation complex via silver pi interaction, and the coordination sphere of a metal cation is completed here either by triflate anions or by the peripheral nitrides. Replacing the triflate anions by less coordinating anions, such as tetrafluoroborate or hexafluoroantimonate, we obtain a 3-dimensional system where once again we have a silver pi interaction and interaction with the nitride to the silver. So it's interesting to note that actually this is the complexation of the bis dipyrrin to the zinc 2 cation that does pre-organize the 2 tetraperiodic strands around the metal centers and organize them with respect to one another for subsequent complexation of silver 1 cations. It's also interesting to point out that not only do we organize the periodic system in this case, but also the peripheral coordinating unit represented here by the R groups. So we thought that maybe we could use this feature one step further and see whether we could only use the pre-organization of a periodic system for the formation of coordination polymers. In other words, to prepare a derivative where we do not have an heteroatom at the periphery and try to build coordination polymers only using the silver pi interaction. Another thing we were trying to determine is whether we could use the pre-organization of a peripheral group. And in this case, we introduced large aromatic units such as anthracene to see whether this could be used as pocket for complexation of silver 1 cation. So this helicate had been described by the group of Maida in the literature, but its assembly with silver 1 cation had not been described. So we went on to re-prepare this compound, studied its assembly with silver 1 cation, and after a rather long time of optimization of the crystallization conditions, we were able to obtain a 1-dimensional coordination polymer that is being formed by complexation of a binuclear silver triflate unit via silver pi interaction between the 2 strands of the helicates, forming thus this 1-dimensional chain. By playing with the solvent conditions, we were also able to obtain a 2-dimensional network in this case, where we have, in this case, not 2 silver cations per helicate, but actually 3 cations per helicate, giving this 2-dimensional architecture. So you can see here the case, how this is organized for a 1D case and how this is organized for the 2D case. We have also obtained a 2-dimensional network with 4 silver cations per helicate, playing with silver perchlorate in this case. Then we went on to investigate the role of a peripheral group at the periphery and try to see whether its pre-organization by coordination of a tetraperiodic system to the zinc 2 cation could be used for complexation of silver 1 cations. We prepared this new helicate, as you can see a crystal structure here, and studied its complexation towards a silver 1 cation. And we have in this case silver pi interaction with the anthracene group at the periphery, not with a periodic system. So we have a system that is rather analogous to what had been studied previously with polyaromatic architectures, but in this case, this is involving a metal complex, in that instance an helicate. So we went on from observing this serendipitously at the beginning, the formation of silver pi interaction by assembling zinc 2, copper 2, cobalt 3 complexes with silver 1 cations, and observe, or sometimes we did not observe this interaction with silver cations. We moved on then to bis dipyrrin again to observe in a recurrent fashion the formation of silver pi interaction with those linear helicates. So current work actually is focusing on the preparation of such network with a whole variety of different linear helicates. Also, we are trying to investigate what is the role of how the bis dipyrrin interacts with a silver 1 cation alone. And actually, we have indication that there is silver pi interaction in this case too. We would also like to extend this study to copper pi interaction, which had been observed in some natural system as well as some synthetic compounds, and also try to see the impact on the photophysical properties of those compounds, as those helicates have been reported in the literature to actually be emissive. So before I conclude, I would like to highlight some of recent examples from the literature involving this silver pi interaction with pyrrolic compounds. There is this very nice work by a Polish group where they prepared a dipyrrin that is bearing at the alpha position and confused porphyrins. And upon assembly with silver tetrafluoroborate, what they observed is a rather complex architecture with silver pi interaction of a dipyrrin fragment. Also, there is a very recent report that has been published online about 2 weeks ago by the group of Mani with a pyrrole derivative bearing a bis phosphinimine ligand. And upon a complexation of copper 1 or silver 1 cations, what they observed was that there was indeed an interaction in this case of a silver to the carbon nitrogen bond, unlike what we had observed in all our examples. Finally, one recent paper that suggests that this type of interaction can be employed for different applications. The group of Kuhashi and Matsubara tried to see whether complexation of a porphyrin towards a silver 1 cation could modulate the sigma Lewis acidity of this type of salt and impact its activity for catalysis. Finally, I would like to thank all the people involved in this work. A large portion of this work has been done while I was in the group of Professor Hosseini. The students highlighted in blue here are all the ones that have been involved in this work: Domingo Salazar Mendoza, Antoine Béziot, Hervé Ruffin, Antoine Mazel, and Fan Zhang. I've produced all the work that that I was lucky enough to present to you today. I'd like to thank my current co-workers that I'm working on different projects at the moment. I also like to thank Hubert Chevreau from the Soleil synchrotron, which was very instrumental in the redetermination of a crystal structure of a compound developed by Ma. I would like to thank the different funding agencies that supported us throughout the years. And once again, I'd like to thank the organizers and you for your kind attention.
So many thanks, Stephane.